Okay, thank you very much. And first of all, this is work that is led by my PhD student, Ori Levi-Rothbein, who's sitting back there. And it's her PhD project, part of it. And I'm very excited about it and very excited that she let me talk about it here. Okay, so I changed the title a bit to be a bit more provocative and speculative because that's fun. So a cognitive explanation for Zipfian distributions in language, and a less speculative title, low entropy is beneficial for language learning. So the big questions we're interested in my lab in general is how do we learn language? And in particular, what is the interaction between learning mechanisms and the kind of input that learners receive, and how this kind of feedback or cycle can explain various outcomes, differences between kids and adults, and also how languages are structured in general. And in this project, we're interested in the question of learnability. So what makes a linguistic input more learnable? And in particular, in the impact of entropy on language learning. Now, what is entropy? Very coarsely defined, a kind of measure of how predictable the environment is. Okay, so environments that have lower entropy are more predictable. And what we're interested in is whether this lower entropy is beneficial for language learning in particular, and whether it may actually impact or shape over time how words are distributed in language overall. Now, why is this interesting? Because words have a kind of odd distribution in language. What does that mean? Words follow a Zipfian distribution. So this was first captured or described in Zipf's law from 1936. He has an impossible name to pronounce, but I'm working on it. And the basic intuition is that a word's frequency is inversely proportional to its rank. What does this mean intuitively? The frequency of words in natural language is not uniform. We don't hear all the words an equal number of times. But instead, what we have are few very high frequency words and a lot of very low frequency words. Okay, and importantly, this kind of distribution has a relatively low entropy. It's more predictable, right? Because we have a few very frequent words. So this is what it looks like. If we look at the words in English, we plot their frequency, we see there are few words that are really very, very frequent, the, of, and a lot of words that have a kind of low and similar frequency. But what we also see is that those frequent words follow a kind of power law distribution. So the second most frequent word appears half the number of times of the first. The third appears half the number of times of the second. And this really doesn't have to be the case, right? It's one particular distribution, but it is weirdly found everywhere you look in language. Okay, so this kind of distribution, that kind of power law, is found across languages. It's found for grammatical categories. So if we look only at nouns or only at verbs, we see the same distribution. It's found for things which seem kind of bizarre, like number words. So if you look at the use of number words, 1, 2, 3, 4, and so on, they're also Zipfianly distributed. SRS is the use of planet names, element names, okay? Made-up characters when we elicit stories from participants. And actually, you find this distribution across many aspects of the physical world as well, including things which are kind of hard to explain, like crater size on the moon or the population size in American cities. All these things follow a Zipfian distribution. Okay? Now, I'm focusing here on why this happens in language, because for other things, the explanation may be very different. So why are such distributions so prominent in language? And there have been many, many, many different explanations, mathematical, communicative, things from physics, and what we're interested in is a possible cognitive explanation. So can it be that these distributions are beneficial because of their lower entropy, that they benefit learning? And if so, okay. So the question is, does lower entropy facilitate language learning? Okay, now this is interesting, even if we don't take into account Zipfian distributions, as a way to get at what learners are sensitive to in the structure of their environment. So to address this, we did a series of studies on word segmentation with adults and children, asking whether language learners are sensitive to word entropy and whether low entropy is beneficial for language learning. And we used a much-used paradigm called statistical learning, which you've heard about before, basically our ability to detect regularities in the environment. And we're focusing on the case of word segmentation. Okay, this was kind of the first paradigm used in language learning in this domain. So basically, the basic finding is that infants, children, and adults can use the transitional probabilities between syllables as a cue to word boundary. Okay? And this has been taken as evidence for the role of statistical learning in language. And this is what an usual experiment looks like. Okay, you hear a series of unsegmented syllables. Actually, there are words hiding in them, and the only cue is the transitional probability between syllables. Okay? This has been studied extensively, one may say over-extensively, in the study of language. And what we found interesting is that all of these studies use a uniform distribution. So all the words appear equally often, even though this differs dramatically from how words are distributed in language, and even though it has the maximal entropy. So it is the least predictable environment. Okay? So what we wanted to ask was whether, if we reduce entropy by changing that distribution, we can facilitate word segmentation. And we did a series of studies on children and adults looking at different levels of entropy. We changed entropy by making one of the words more frequent, so a very simple manipulation. Okay, so we have high entropy, which is the uniform distribution, the usual one, medium entropy, where one word appears 55% of the time, and low entropy, when one word appears 80% of the time. Okay, and our predictions were that low entropy will show better segmentation overall, and also for the low frequency words. So it's not really interesting what happens to a word that appears 100 times, but if we can facilitate what happens to the word that appears only 9 or 19 times, that will be kind of more impressive. So we used a standard word segmentation task. There are 4 words in this unsegmented speech stream, and we had 142 adult participants and 130 child participants. Please note the high numbers of child participants. This is thanks to Ori's hard work. And we compared these 3 conditions. Okay, high entropy, each word appears 32 times. Medium, one appears 71 times. The other 3 appear 19 times. And low entropy, one word appears 101 times, and the rest appear only 9 times. To give you a feel for what that sounds like, no, I will not give you a feel for what that sounds like, apparently. Okay. You kind of get the pattern, right? Okay. Okay, so what were the results? Let's start with adults. So when we look at segmentation accuracy overall, yes, indeed, accuracy is much higher in the low entropy condition. Okay, and the medium entropy really isn't doing much. But maybe this is driven only by them having learned the very frequent word. So we look only at the low frequency words, and we see, again, a facilitation. So in the low entropy condition, the low frequency words were learned the best, even though they appeared only 9 times. Now, this is a really high accuracy rate for these paradigms, which usually tend to be kind of not great in the learning accuracy overall. Okay? When we look at the relative impact of frequency versus entropy, we see 2 interesting effects. So, of course, the more you hear a word, the better you are at learning it. But what matters isn't the absolute frequency, but the relative one within the condition. So a word that appeared only 9 times in a low entropy environment was learned as well and even a bit better than a word that appeared 71 times in the medium entropy condition. Okay? So now, what did the kid data look like? And it looked very similar. So the numbers are a bit lower, but again, accuracy overall is better in the low entropy condition. And importantly, this holds when we look at the low frequency words. So kids are at chance. They're not learning the low frequency words in the 2 other distributions, but they're learning them at pretty good rates in the low entropy condition, again, despite having appeared half the number of times. Okay? And we see the similar effect of this relative frequency matters and not the absolute one. Okay, so what did this tell us? We've seen that reducing entropy facilitates language learning, but only when entropy is reduced enough. And interestingly, our low entropy condition is similar in entropy and information to what actual language looks like. Okay, the medium entropy actually has a higher entropy than when you look at the words distribution in a language. This has methodological implications for statistical learning research by suggesting that we're actually probably hugely underestimating learning because we're assessing it in suboptimal conditions, conditions which have the maximal entropy. And it's consistent, not proving, but it's consistent with a cognitive explanation for Zipfian distributions. And this is the link that we're working on right now. So there are, of course, many open challenges in future directions. One of them is it about entropy, a certain level of entropy, or about the actual power law Zipfian distribution? And that's what we're looking at now. The other is extending these to other language learning tasks, and Ayelet is giving me the look, which means I have to stop. So I will stop, and thank you all, and especially Ori for pioneering this work.